Hello. So this is the demo for the advanced JAX, for neural network. So earlier we have gone through the fundamentals of JAX and its comparison with NumPy. Now let's see how to build a proper production ready code using JAX. So this is the cheat sheet of what functionalities JAX provides. So first is we can create a tensor using an array. We can have there are some special functions like all zeros, all ones, identity matrix, like that. Then we can create random keys using this prng key function. Then we can split, we can normalize, and yeah, and the the tensors are immutable. So then we have this git function, which is for compilation. Then we have grad for calculating the gradient. Then we have value and gradient, which is to get the values and evaluate both value and the gradient. And then we have vmap, and we have pi trees as well. So it creates a tree kind of a format, uh, and it applies function to all leaves. This function applies function to all leaves, and this one gives all the leaf values. And then we have neural network primitives like params, um, loss and grad. Are like, this is how loss and grads are created. And new parameters, if you want, we can use it like that. Then we have flax, linen. Excuse me, I'm so sorry. uh, so we can create a module. So this Flax is a neural network library, and Linen is the still main module style API for defining model. So it's a high-level neural network library built on top of JAX for flexible research-oriented modeling, and it's object-oriented, and yeah, it has a lot of functions. So this is how we can create a network, and yeah, this is how we initialize it. This is how we do the forward pass, and this is for creating the gradient, and this is to initialize the gradient and then update it. Then this is for training, and apply gradients is to apply backpropagate and apply the gradients and get back the values. Yeah, so that is it. Then we have this comparison, which is so PyTorch and JAX primitive and Flax. So as we know, the NumPy is very basic. It is good for small data sets, but when you are handling complex, heavy data, then we need to go with something which supports GPU, which is something like PyTorch, JAX, NumPy, or sorry, TensorFlow or Flax. So JAX primitives is the very basic functions, but Flax is a neural network library built on top of JAX. So yeah, we will see that the difference of these three. So yeah, these are the values. So JAX best practices is uses JIT everywhere. Excuse me. Sorry. Sorry about that. So it uses JIT everywhere. JIT is JIT stands for just in time compilation, so which optimizes Python functions for speed by compiling them into efficient XLA code at runtime. So how it works is it traces a function's operations on input stage shapes to create a static computation graph and then compiles it for hardware like GPUs or TPUs. So this fuses operations and reduces Python overhead and enables aggressive optimizations. Uh, So, yeah. Uh, then we have, PyTrees. It handles random keys properly, writes pure functions, so that there are no side effects, no global state. It uses VMAP for batching, so we don't have to write loops over batch dimensions. It automatically handles the batch. Then we have compose transformations, and it uses opaques for optimizers. Yeah, that's it. Then let's create something using JAX. Yeah, let's create this thing. So this is how we create using the NN, torch.nn. We create it like this. Now yeah, let's using the JAX, let's do the let's handle the moons classification data. And so how we'll do is we'll create random keys first, then we will define the batch size, how many n per class we have to run. Then we got the input. We are now stacking the data, which is oops, sorry, my bad. It was Z. This is the moon 1, this is moon 2 data. Then we are concatenating it and creating one data out of it. And then we'll first split the data. Excuse me. Then we'll so this is basically creating the moon data. Then we are splitting the data into train and test, and then we will call this flexible MLP, which we defined over here. Like this is where how we want our model to work, the sequence, how it should take the sequence. So yeah, that is happening over here. The input layers, where is that? Yeah, it will create a dense layer, and then apply the activation on top of it, and then return the output. So it's a very simple neural network we have created. And now once that is done, we will start the training, and it will run for over 200 epochs, and it will calculate the loss, validation loss, test and train loss, and then it will give us a proper matrix. So let's see how it looks. So as you can see, as the epochs are increasing, the loss is decreasing, and the validation loss is increasing, as you can see. So here you can see the graph. For the training this blue line is the training data, so data's performance. So here you can see the loss is going almost to 0, which is a good sign. But when we when we validated it against the validation data, which is the data the model has not seen before, so you can see it is randomly giving the values, and the accuracy is increasing. Loss is increasing. Ideally it should also decrease, but this is increasing, and it should come down, but it is increasing. What that means is it means that the model has overfit on the training data. It is giving so good values on the training data that it has overfit on that, and once it sees the new data, it is not able to capture the correct output. So this is what overfitting looks like. Now let's do the XOR with flags. So we'll again create a layer, the same layer MLP will use, and then we'll give it. These are the input data. We'll give the input data to it, and here we'll for activation we'll use stan, and let's see how it works now. So for this, the training loss, you can see it was high initially, but then as the epochs increased, it reduced. Same. Yeah. So now let's create a complete flags training pipeline, which is yeah, let's create a using NN model. We will create a template for our model. We'll have define the activation function. We will we want a dense layer, and then apply an activation function to it, and then return the output. And yeah, this is to create the split train and test data. We and yeah, once we this is the single training step, and this is how a complete flags pipeline is created. Here we are also, it's a binary data, we will calculate the cross entropy, binary cross entropy. And let's move to the next part. Then for optimizers, here we have different options again, like we did in PyTorch and TensorFlow. We have stochastic gradient, we have stochastic plus momentum, ADAM-W, RMS prop. These type we can use like as per our requirement, and we can also provide the learning rate to them. A learning rate is like a step. Now, how many steps do you want your gradient to take to find the local minima? And yes, these are the. Now let's use FlagsLinen to build a very basic module. So again, we'll use the NN modules. We'll inherit the values of NN module. In the call, we will define our layer. First, we want a dense layer. Then we'll apply an activation. Then again a dense layer, and we'll give the output. This is how we want it to be. So yeah, Flags uses the NN.module with an NN.compact decorator. This decorator, and yeah, this is then becomes very similar to PyTorch's NN module. So then you can call it like this. So yeah, we'll create an instance of the model, initialize the parameters, and we'll call it, and yeah, this is actually the tree. How the layer will look. So first will have a dense layer, then bias will apply to it, then a kernel, then dense 2, which is again bias and a kernel, like that. So now let's look at the high level flags API with high level API with FlagsLinen. So Flags is Google's neural network library for JAX, and then it's modern API which uses object oriented implementation. And let me this is the very basic module. You have to remember that to use this decorator to use, so then you can use it as a PyTorch NN library. Now initializing the parameters. So yeah, JAX has these functionalities like a random, JIT, value and grad. So we'll be using that. So this is for initializing the variables. This is for the forward pass. So in the forward pass, we want to do the matrix multiplication, add the bias, and apply the activation function and return. So it will do that. This is for calculating the loss function. For this, that was for mean square error. This is for cross entropy, categorical cross entropy. Then this is the create training step. So create a JIT compile training first step. So this is the JAX pattern for efficient training. So what it does is the first call compiles and caches based on the input shapes, and so the repeats are faster. So that is the intention behind it. Then we have the train MLP, in which we will the training loop which we call. So we'll call the forward, then we'll apply the loss function, we'll calculate the loss, and then do the gradient calculation, and then we'll do the gradient calculation, and then apply the gradient back to the values and again do the training. So that is what is there. We will now use it for XOR problem, and here you can see that this initially it was really high, but as the epochs are increasing, the loss is approaching to 0. Now let's see the training loop in a functional style. So this is the gradient for gradient calculation. This one is for calculating the loss and how the training should work in each epoch. And yeah, that is pretty much it. We can create a neural networks from scratch using the JAX primitives as well. So yeah, I think we did that earlier. I will skip that for now. Then primitive style loss functions, you are again writing the formula down and creating the functions and reusing it whenever required. And then same for activation function, you can write it from scratch and use it as a function and use it wherever required. And then yeah, this is for gradient calculation. So excuse me. So this is the gradient calculation. So this is the function where the values are calculated, and for each value that the particular table of what values needs to be changed is formed. Then we have gradient with pi trees. So we can use the pi trees. So JAX can differentiate through nested Python structure, which is pi tree, and this is how the neural network parameters work. So you can visualize how the the backpropagation is happening. So let me just go there. Then yeah, again we can do how to use value and grad and get both the values at the same time, so that you don't have to separately compute it. So for that we have this function, value and grad. Then we have basic differentiation. Again we can do it. Let's say this is our equation, simple scalar function. Then yeah, we do grad 1. So these are higher derivatives. This is second order, this is third order derivative of the of f. So this is how you can apply it. If you do it once, that will be first order derivative, which is this one. So again you can do it, and then you can apply a loop on top of it to find out at a higher dimension differentiation. So this is how it is done in the very low level area. So then again we can do, we saw grad value and grad, and we can also create Hessians and Jacobians. Jacobians are the first order derivatives, and Hessians are second order derivatives. Then yeah, okay. Then again, these are the fundamentals of JAX. So it has special arrays like all zeros, all ones, identity matrix. We can create it out of a range as well. Key, subkey, splitting the data, splitting the key over a value. These are the operations. Random key generation using this. It takes care of shuffling and reproducibility as well. These are the data types supported. Device management is using that. If you want to use GPU, it will detect your GPU and use it. We can do element wise operations on top of it. We can do matrix operations on top of it, like matrix multiplication, transpose, inverse, and then we can also use reduction operations on top of it, some by column, some by row, mean max, argmax, like that. Then yeah, we know that it is immutable, so if you want to create, it will create a new value and then point it to it. Then JIT is just in time compilation, grad is automatic differentiation, VMAP is for automatic vectorization, PMAP is for parallel mapping. Then we have, yeah, these are, I think, this is how we compute the transformations. We are taking a grad first, then we are doing a VMAP, excuse me, and then we are doing a JIT, and then we can also again do the Einstein summation on top of it. We have to just provide the subscript and the tensors on which the operations needs to be taken, and it will do the operations. So any complex operation can be, you write it in this format, and it will do. So you don't have to again write each operation one by one. Just give it what you want in the output, and the back computation will happen. Okay, thank you.